Let's remind ourselves of the overall point of the example that we had last week, because it was kind of a long time ago, because we had not Flux Day. Flex Day on Thursday. Flux Day was Wednesday. Flex Day was Thursday. And then it was Friday, Flex Day on Friday. So the last time we talked about flux was the previous Flux Day. So if you would recall, we had water flowing through a pipe, and we looked at the water flowing through a cross section. We started off with a perpendicular cross section. So the vector of the water is perpendicular to the flat area. Then what we did was we angled that area. We kept it, we just angled it in one direction. So we angled the cross section, which created more area. So the area there increased, but the flow perpendicular to that area decreased by the same factor. I don't know, decreased by the same. We multiplied by the reciprocal. So our flow perpendicular to this area is no longer just all of 5 flowing perpendicular to the area. The flow perpendicular to the area is going to be 5 times the cosine of whatever angle we angled our cross section. But the area is also increased. So we reduced the flow perpendicular to the area, but we increased the area through which the water was flowing. So we multiplied by 16 divided by the cosine of theta. So that was one of the interesting things that came up last time. If you angle the area, you divide by the cosine of the angle. And that's how the area increases. And then the 2 cosines cancel out. So the angle didn't actually matter. And we ended up with 80 cubic centimeters per second, which is supposed to represent the flux through the pipe. So it shouldn't have changed. That was the thing that we wanted to point out. We noticed that this is what we expected to happen, because how we're measuring the amount of water flowing through this pipe shouldn't change based on whether we're measuring at an angle or we're measuring perpendicular. These are supposed to be the same amounts. So we got the same flux, and this was as expected. This is what we wanted to have happen. There'd be a flaw in our thinking or our method if they didn't come out the same, because what this is intended to measure is the flow of water through the pipe. The water through the pipe is not going to change and slow down or speed up if we change the angle at which we're measuring the water flowing through the pipe. Okay. I think when I originally presented this problem, I was trying to do too much shit. I had the square pipe and the circle pipe. You know what? Let's just do the area. The square pipe was so that we could get at this cosine of the cosine angle. So the natural progression is, since we have this, we're dividing by the cosine of theta, and that makes the area larger. As theta increases towards 90, as theta approaches 90, the cosine of theta is approaching 0. And so the area of the cross section is approaching infinity. We're taking 16 and divided by a smaller and smaller amount. So that's another thing that we want to point out. As theta approaches 90, degrees. I probably in Calc 3 should be talking about pi over 2, but I also have a trig class, so we're going to go with 90. The cosine of theta is headed towards 0. And so we're taking 16 and dividing it by an increasingly small number. And so this limit is going towards infinity. Also, the cosine of theta is going towards 0. So the flux perpendicular to the surface is going towards 0 as this angle keeps getting closer to flat. But when theta equals 90, we are no longer measuring the flow of the water through the pipe because our cross section is just running parallel through the pipe. Yes. Uh-huh. Not quite. What we're canceling out here, what we're kind of canceling out here is 0, because what's happening is this denominator is going to 0, and this numerator is going to 0. So we have a 0 over 0, which is indeterminate. So sometimes 0 over 0, we can't say will cancel out. So I was being a little bit suspicious. It was very fishy for me to be like, I'll just divide by the cosine of the angle. And no one raised the question, like, well, what if theta is 90? And that's what we're covering right now. So when theta is 90, we get this 0 over 0 indeterminate situation. Dividing by 0 is undefined, but 0 over 0 is indeterminate, which means sometimes 0 over 0 is going to be constant, and sometimes 0 over 0 is going to be infinite or negative infinite. So it could be weird things happen in indeterminate forms. Anything covered that you would want to use L'Hopital's rule on, that's an indeterminate form, and that means stuff is fishy. So it's not completely undefined, although no one would fault you if you said undefined, but we should say when it's 0 over 0, that's indeterminate. So what we're looking at here is this cosine of 0 going to 0, this cosine of theta going to 0, and this numerator cosine of theta going to 0. So the area is going towards infinity, and this velocity perpendicular to that area is going towards 0. So this is kind of a 0 over 0 situation, or it's a 0 times infinity situation. So we've got to think about what's going on at 90. Does the problem still make sense at that point? It's kind of like when we were back in Calc 2 days, when you were finding the integral of convergence for a power series. The only reason I think I'm making this connection is that right now, my Calc 2 class is finding the integral of convergence for a power series. So when you end up with things that aren't going to give you an answer like 0 over 0 or 0 times infinity, where shit just doesn't really make sense as far as numbers go, we have to look at that case individually. So what does it mean when theta is, when we can no longer make this calculation, does this still fit with our understanding of the situation? And the answer is yes. This still fits with our understanding of the situation because we're trying to measure flow through this pipe. We can't do that if we have a cross section that is just going along with the flow, because our velocity vector, our water, is no longer flowing through our cross section. So at 90 degrees, the water is no longer flowing through the cross section that we're trying to use to measure. So at theta equals 90 degrees, at theta equals 90 degrees, we're no longer measuring flux through the pipe because it's flowing parallel to the surface that we're trying to measure. The problem is set up to measure the flux through a surface, but the water is no longer flowing through the surface. It's flowing along the surface. So the flux through is zero. So in this situation, 0 times infinity is 0. That is super fishy to say it that way, but we're all advanced calculus students. And we get to say fishy things like 1 divided by 0 is infinity, rather than 1 divided by 0 approaches infinity. If we're coming at 0 from the positive side. Good question. Any questions, comments, snide remarks? How's everybody okay? Everybody looks very sad today. Like, oh, I thought we were going to talk about dogs the whole time, and now we're talking about math. That makes me sad. Can't we just go do our homework and then talk about something else in class, like have nap time or something? Yeah. Yeah, that. It never works for me either. Like in car ride, if there's going to be a long road trip, I might as well just drive the whole time because I cannot sleep in the car. I'm not going to be sleeping in the car. That would make the driving a little bit exciting, though. I do get indications every once in a while that I should stop and sleep. And so, but that's how far it has to go. It has to be the point where it's like, oh, no, I am literally nodding off and trying to drive. You know what? I'm just going to pull over and sleep for a little while. So I guess eventually, physiology takes over. And you're like, all right, physiology, you win. I will go to sleep. But if it's like, oh, hey, why don't you go take a nap? I thought, that's not how this works. It's the daytime. I'm going to be awake. I'm just going to sit there, and by the time I fall asleep, I'm going to have to get up. But anyway. So some of the other interesting things that come up that are adjacent to this is taking a thing that we know, the area of a circle is pi r squared. So, and the equation for a circle is x squared plus y squared equals r squared. We're just going to go with the rectangular coordinates, even though we have better coordinates for describing round things. We know that x squared plus y squared equals r squared. The reason that we want to go with x squared plus y squared equals r squared is that we want to take our circle and think about an ellipse. Now, our equation for an ellipse is x squared over a squared plus y squared over b squared is equal to 1. This is typically how we write the area of an ellipse, which is very different than the way we write the area of a circle. Apparently because we like things that are very similar to look very different, at least at the time that we're introduced to these things. Now, we know what's going on in the area of the circle. R is the radius, and we know what the radius of the circle is. That's just how far it is, in this case, from the center, or in this case, the origin, to any point on the circle. If I have my rectangular coordinates, we have R units out here, so R, 0, and negative r units down here, negative r 0, because that's how things that we call radius work. Up here we'll have, or down here we'll have 0, negative r, and up here we'll have 0, r. When we're looking at the equation of ellipse, x squared over a squared plus y squared over b squared equals 1, we're just looking at a squashed circle. The ellipse is just a squashed circle. I don't know why I can make them kind of flat on the top and bottom, but I can't make them not really pointy at the ends. I think it's because I'm American and that's what American footballs are shaped like. I don't even like football. This is one of the reasons why. American football has decreased my ability to draw a proper ellipse. So when we have an ellipse, the thing about an ellipse is that it's kind of like a circle in that it's round-ish, but it has two radii, which means they can't be radii. We can't call it a radius, but it has these two radii. It's got a distance on the major axis and a distance on the minor axis. We've got a major axis and a minor axis. So up here, I have a and negative a on these sides. So here's a 0, and here's the point negative a 0. And if we make y equal to 0, we could see why that's going to be. Then x squared has to equal a squared, so x can be plus or minus a. Then the same thing happens on the minor axis, just the way I've drawn it. B is smaller. So here's going to be 0b, and down here will be 0, negative b. So an ellipse is a circle with two different radii. But a better description might be to say that a circle is a particular case of an ellipse. A circle is just an ellipse where A and B are the same. And if we rewrite our equation of a circle to have this 1 on this side, we have x squared over r squared plus y squared over r squared is equal to 1. And so really a circle we could think of as just an ellipse where A and B are the same. The major and minor axis are the same. The thing that I like about this is that we can take this this concept and we can also pull it out of the area of the circle, which is pi r squared. The area of this ellipse, if we have it in this form, we know what the length of the major and minor axis are. We know what I know this is bad language, but the two radii are. And the area of an ellipse is just the same, but we have different values in each of these directions. So really when we talk about pi r squared, we are finding the area of an ellipse as well. It's just that in a circle, the horizontal and vertical radius is the same, and in an ellipse, they're different. But we're still just taking pi times the product of these two radii. So instead of having same here and here, we've just got different. A B here and an A down here. If we make those the same, then we get the familiar circle, which is pi r squared. The area of an ellipse is pi times A times B, where A and B are the big radius and the little radius. And this happens a lot where we use the same, where we have very similar things. For example, the area of a square is the side squared, and the area of a rectangle is length times width. A square is just a rectangle where we're taking the length multiplied by the width. But the length and the width happen to be the same. So instead of having our square down here, where the length and the width are the same, we have different values. We've got a length and a width. I made this one wider than it is tall. So it made more sense to call that one the width, even though it's smaller. Looking at it from this perspective, that is wider. I guess it depends on what tradition you come from. So no, the length has to be the longer one. It doesn't. No matter how I label this, someone will be angry. They'll go, no, the length needs to be the longer one. But if I put them the other way around, it's like, oh, that's not the length. That is clearly the width. We're looking at it from this angle, and it's clearly the width. And then some dude stands over, no, I can see the width is here, and then I can see the length long side. So it depends on where you're standing, I guess. And then some other person over here is like, oh, no, I think this is a snake. And I go, dude, that's an elephant, and you have the trunk. The rectangle we're talking about is way over here. It doesn't matter. It makes my wife real angry though. So go measure the desk so you know how big it is. I come back with the 3 measurements. And I happen to know that if I'm measuring this desk, I know which one is this longest one is going to be this one. It's like, oh, which one is the width? Oh shit, I didn't measure a width. I measured a radius, a depth, and a height. So what's the height? It's like 8 feet. Well, that's not the height. It is if you stand it up. Actually, I don't do that because I know it pisses her off. I've done that joke. And so I can put it away. Although I can't not, when my mom talks about hearing, say, huh? Well, I don't think he heard me, huh? I don't think he heard me, huh? I usually get at least 3 huh in before she like smacks me. So I can't not do that. Any questions? So circle is actually we think of a circle as its own thing, but really a circle is just a special ellipse with this where everything's the same. Just like a square is a rectangle where everything's the same. It's like a square is just a boring rectangle, just like a circle is a boring ellipse. The interesting thing that we've also found out is we know that we take a circle, if we have this circular pipe, we know that if we have the area, if we go perpendicular, we get a circle. But if we start angling off, if we angle off, we get an ellipse. So we can figure out how much of an angle we have to make to get a particular ellipse. So because of the area, we know how much area we're going to get. So we can just take the pi r squared and divide by the cosine of the angle that we're looking for. And then we can figure out whatever ratio of A and B we want. So we can figure out what angle that ellipse is going to be at. So that's an interesting connection between the area of the ellipse and the area of the circle. And the angle you need to transform one into the other. I know this doesn't seem very calculus, but that's not this class is, even though it's normally called Calc 3, this is calculus with analytic geometry 3. So there's your analytic geometry for the week. We have to do the analytic geometry too, and there it is. Also, because most of the time I ask for the area of an ellipse, and some people start writing the equation, solving for y, and finding the area under the curve. And I go, whoa, that's a little bit excessive. And the students be like, oh, you son of a bitch, that's what you asked us to do last semester. You're right. You're right. But we were supposed to find this out so that we didn't have to do it all. Any questions? Comments? Deep thoughts? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.